Alright guys, so today I'm going to start your learning about circular motion. Alright, and so I'm going to actually start you off with a question. Alright, so take your time, answer this question. Race car is driving around a circular racetrack with a constant speed of 100 miles per hour. The car is... And take a minute, pause it, think through the question, convince yourself of an answer, commit, and then go ahead and unpause it and get the answer. Alright, so by now you should have answered. The answer, of course, is that it is accelerating. Now you have to remember that this is because if it's going around a circle, even at constant speed, it was very important here that it says constant speed because the velocity is changing, right? Because velocity is a vector. So at the top, I'm traveling this direction. At the side, I'm now traveling this way. My car is always changing direction. If it's always changing direction, then your velocity is changing. And if your velocity is changing, that means it's accelerating. So you need to remember that acceleration means a change in direction. All right? So any circular motion means that your object is constantly accelerating, whether it's changing speed or not. All right? So here's a couple of things that we know travel in circles. You got fairground rides. You've got the moon going around the Earth. You've got this rock on a string being swung around. All right? So these objects are often at constant or close to a constant speed, right? But what does Newton's first law say? Well, Newton's first law says that an object will maintain its state of motion, meaning that it will maintain its current velocity, both magnitude and direction, unless a net force or unbalanced force causes it to change, unless something else makes it change. Okay? Now, in all of these situations, whether it be the fairground ride or the moon or the rock sliding around, these objects are not maintaining their state of motion. So in order for them to change their state of motion, to change direction, there must be some kind of force acting on them. Okay, there must be something else that's causing them to change whatever they're doing. All right, and so we're going to talk about that a little bit more today. But first, a little bit of maybe nature of science, theory of knowledge. How do we know the Earth is rotating? Okay, go ahead and pause the video. Think about this for a couple of minutes and then unpause it and I'll talk about that a little bit. Okay, so hopefully you've kind of thought about how we know it's rotating. A lot of times people say, well, we look up at the stars, but that's not really valid because the stars could be moving, right? We only say that we're moving under the stars because that's what we've been taught. So how do we know the Earth is actually rotating around its axis and it's not just the rest of the universe that is moving? Well, the best that we can do is something called, at this level, the best we can do is something called a Foucault pendulum. Okay? So a Foucault pendulum is set up as in this drawing right here. And what it does is it has a very, very long string or rod, very light, and then at the end it has a very, very large, very massive ball or whatever at the end. Now, what happens as it swings is that it swings very slowly. And as it swings over, if the ground is rotating, because of the length of the string, if the ground is rotating under it, then when it swings back, it's actually going to swing back in a slightly different location than where it started from, because it will maintain its forward and backward momentum, just going forward and backward. And so if the ground moves under it, then it will actually rotate. And you'll see this kind of diagram like the star where it starts here and it goes that way and then it comes back and then it goes over and then it comes back. And so it slightly moves every single time. Now, on Earth, it takes us about 24 hours, though it's technically not 24 hours, it's a little bit less. It's a sidereal day. But we don't need to worry about that now. The idea is that it would take approximately 24 hours for this star pattern to go all the way around to where it started again. All right? Now, of course, that would work very nicely at the North Pole, where the Earth is actually rotating in a circle around it. Anywhere else on the Earth, though, you can still do this. It's just the effect is not as great. It might take it longer than a day to get all the way around. And so that has to do with your latitude. And you can read up on Foucault pendulums if that's interesting to you. But that's an important idea because that's a way that we can see that force associated with the spinning, the turning, the motion. All right? Anyway, back to circular motion. So we're going to actually start to put a little bit of math with this before, I guess there's a little bit of math we need to understand before we start really talking about those forces that are causing this circular motion. So the first thing you need to know about is something called radians. Okay, well, first, let's talk about this. Why exactly are there 360 degrees in a circle? Who in the world came up with this number, 360? I mean, why? And you're going to say, well, because a right angle is 90 degrees. Okay, well, why the heck is why is right angle 90 degrees? Why can't it be 100? Wouldn't 100 be nicer? Right? Or, I don't know, there's a lot of numbers you could come up with that would be nicer than 90. Okay? So why 360 or why 90? Well, the answer to that is that these degrees were come up with by the Babylonians. Okay? So a long time ago. And what they noticed is that the Earth took about 365 days to go around. And so they said, well, let's just say that each day the Earth goes approximately 1 degree. Now, 365 is kind of an ugly number and difficult to work with, and so they said, well, I could make it much nicer by calling it 360 degrees. It doesn't match up with days anymore, but you got 360 degrees. That splits to 90. You know, you got the 30, 60, 45. You got a lot of nice numbers in there that end up working well with the mathematics, though still slightly annoying because 360 has nothing to do with the circle itself. 360 has something to do with the Earth, right? Which that number never would have been come up with on some completely different planet. And so it's fairly pointless. So we have something that we call radians. Okay? And I don't know how much you know about radians. So I'm going to go into a little bit of detail just so that you understand. Okay? Radians are a measure of an angle. Okay? Just like degrees are a measure of an angle. Okay? 1 radian is the angle that you have to go through in order to cover a distance of 1 radius. Okay? So if theta is 1 radian, and we can show that with a 1c, or you just put a 1 radian is the angle required, again, to go through a length of 1 radius here on the circumference of a circle. Now, you can probably figure out how many radii are there as I go around the circle. Well, you should know that the circumference of a circle is 2 pi r. Now, if the circumference of a circle is 2 pi r, that means that there are 2 pi radians in a circle. So I would go 1, and then I'd go another theta, and then I'd go another theta, and then I'd go another theta. I know I'm not drawing these very nice, so I'd go another theta. That would be another r, right? That's the length of the radius. So I got 1, 2, 3, 4, 5, and then I'd get 6, and there'd be just a little bit left, just enough because 2 pi is about 6.28, so just enough for that to be 0.28 radians. All right? So we can get from this, because we understand that the circumference of a circle is 2 pi radians, that there are 2 pi radians in a circle. So 2 pi radians is equal to 360 degrees. All right, those two mean the same thing, 2 pi radians or 360 degrees. Now, it's common to not put any notation for the radians. You could just write this 2 pi equals 360 degrees, and that's normal. There's nothing wrong with that. It's just how it goes, okay? So we'll talk a little bit more about this later, but it's important that you recognize when we talk about radians what a radian is. It's just a degree. It's how far we're going, and we'll talk about these things a little bit more later. All right, so let's go on to the next little bit here.